you speak a little louder, please?
Louder, okay. Or maybe you can adjust because I don't want to shout. Okay. So I will try to speak louder. And also, if you cannot see very well what I'm writing on the blackboard, don't hesitate to just ask or complain. Or if the camera is not following me properly, please open your mic and just talk. Okay? So the goal, what's the goal? The goal is to describe mathematically a gas which lives on the whole space Rd, the whole space Rd, with infinitely many particles. And when I say describe, I should say the dynamics of a gas, an infinite gas, okay, and the whole space. And we will particularly ask what is happening if we start the dynamics close to an equilibrium state. So starting close to an equilibrium state. An equilibrium state, I mean, it's going to be completely translation invariant, so it's not going to depend on the space variable, but it will still depend, I mean, there will be a velocity distribution of our gas, which I will call F0 of V. This F0 of V could be just a Maxwellian, but could be some more complicated distribution like Fermi Dirac. So here is the picture. So let's see, maybe it's better if I change the blackboard. So I think online you will not see what's people do. I think it's still okay. So the picture is the following. So we have this infinite gas. So I'm here plotting the density of my gas. Okay, so here it is x. Here is a rho of Tx, which I am plotting. So the equilibrium state, my uniform gas, will have a constant density everywhere. And then what I'm doing is I start with something which is a perturbation of this gas. And then I turn on time, I wait, and I try to see what's the evolution of this gas close to the equilibrium state. Okay, so positive density in the title is because at infinity, rho will be strictly positive. I mean, it will tend to a non-zero limit at infinity. It will not go to zero far away. I would like to insist, so here we will look at two models, one quantum, which is Hartree, and one kinetic, which is Vlasov. I would like to insist that in the original paper of Vlasov from 38, that's exactly the problem he was actually looking at. It's a paper in Russian. Actually, I found it. It was in Russian, but there is a translation from the 50s, which you can find on the internet. So Vlasov was exactly looking at this situation, where F0 was the Maxwellian or the Fermi-Dirac distribution, and particles were electrons, so they were interacting with the Coulomb potential. So he wanted to describe a gas containing infinitely many charged particles. Coulomb is, of course, a problem, because it's long range and you have to kind of do some renormalization, whatever. And I think the predictions of Vlasov were not quite right at the moment, so he was actually looking at the linearized problem to try to see what's the long time behavior of this perturbation, and then this was corrected by Landau in 45, who predicted what will happen for a long time, so namely, I mean, your perturbation will disperse and disappear, so it's some kind of a return to equilibrium in a weak sense. Okay, and that's what people now call Landau damping in the context of Vlasov. But for us, it's just dispersive effects which imply a return to equilibrium at large times. So, we will look at these two models, and I will now define the two models. I think many of you know at least one of the two models, but it doesn't really hurt, and many of you know both very well. So it doesn't hurt to remind you of the models. So now let's see if the camera follows me. Even when I speak loud, it doesn't. Oh, okay, good. So let me quickly remind you. So let me put Vlasov on the left side and Hartree on the right side. So first there's the space. So in Vlasov, we work on phase space. So our space is really position and velocities, right? So there will be xv, which correspond to the positions and velocities of the particles. And let me remind you that on the quantum side, the space is L2 of RT. That's the configuration space. Okay. What are the objects in Vlasov? So we are in kinetic theory, so our objects are just positive functions, or maybe even measures, but they will be just nice functions in our case, depending on time, position, and velocities, which give somehow the distributions of the particles at a certain point having a certain velocity. And here, our variable is an operator which is non-negative and self-adjoint. Non-negative meaning that its spectrum is on the positive axis. The plot over there was for the density. So what is the density? Rho f t of x. There will be some 2 pi's floating around because of my convention. It's just that you integrate your distribution over all possible velocities, and then you get the corresponding density. On the quantum side, the rho gamma of x is t and x is just gamma of t, and what you have to do is you have to look at the kernel of your operator gamma. So your gamma must have a kernel, and the kernel must not be too bad, maybe continuous or something like that, to be able to take the 2 variables of your kernel equal, and this is how you get the density. And then the number of particles in your system is just the integral of rho. So that's the integral of rho f, right, which is 1 over 2 pi to the d, the double integral of f. And on the right side is the integral of rho as well, which is just the trace of the operator, namely the sum of the eigenvalues. Okay. In our case, the integral of rho will be infinite because rho will tend to a positive constant at infinity, so the number of particles will be infinite. That's what we want. And of course, I have to write the equation. I think I can still write it here, but then I will just put the blackboard up so then everybody will see it. So Vlasov, there will be a 2 for me, just by convention. Okay, so 2 because the mass is maybe, what is it, 2.5 by convention. And then there is the gradient. Then I will have the mean field potential. And then scalar product with the gradient in V equal to 0. That's the usual Vlasov equation. I will assume in the whole talk that W is a very nice short-range potential. So it will be integrable, and it will even have a few derivatives which are integrable. So very nice short range. I will not at all be able to discuss anything close to Coulomb, and I will actually not even try. But of course, one important question would be to try to study these models for Coulomb or the like. Okay. On the quantum side, so let me write the Hartree equation. There will be lots of h bar because I will soon take a semi-classical limit. If you don't like h bar, you can just discard this now. So it will be I h bar dt gamma, which is equal to the commutator between minus h bar squared Laplace plus double, oh sorry, I will put another h bar. So there will be an h bar to the d, and then W convolved with the rho gamma, everything commutator with gamma. Okay, so I've put lots of h bars. So these 2 h bars here are really because we will do a semi-classical limit. Okay, and the other h bar is more of a mean field type. Okay, so the density will become very high in my quantum system, so I will have to compensate it by multiplying the h bar to the d. So this is more kind of mean field. So we look at the high density regime. Okay? So what is the question? The question is to look for solutions of this equation or that equation in the neighborhood of an equilibrium state. So what is an equilibrium state? So now let's see, I hope the equation is still visible over there. So we want to look at states which don't depend, I mean, translation invariant, they don't depend on space. So on the Vlasov part, it would just be, if you like, an f of t x v, which is an f0 of v. And you have to just sit down and check that it doesn't move. That's something like that. It's a stationary state of your equation. Why is it so? Well, first, let's compute the density of the state. The density is just a constant. It's 1 over 2 pi to the d integral f0. So you see that if your f0 is integrable, then the density is finite, and that's our positive density, that's our positive constant. There it is. Now what you can do is to compute the mean field potential, so W star rho f0, which is then just integral W, this I will call rho 0, integral W times rho 0. Okay, because the convolution of a function with a constant is just the integral of the function. So you get a constant potential. And of course, if you have a constant potential, then the gradient is 0, so you get 0 here. The gradient in x is 0 here. The gradient in time is 0. So you see, it's a stationary solution of your equation. So any function of v, only of the velocity, gives you a stationary solution if f0 is integrable. Okay? Before telling you what are the L0s I will consider, let me go on the right side. So on the right side, an equilibrium will be a gamma 0, which is a Fourier multiplier. Okay, so it must be a translation invariant operator. So the correspondence will be an F0 or minus I h bar gradient. I will put an h bar here. This is what corresponds to this kinetic equilibrium state in the quantum case. If you compute the density of this gamma 0, I mean, you have to compute what is the kernel of a Fourier multiplier. You know, it's just given by the Fourier inverse of x minus y. Then you do x equals y, and so on and so forth. You will see that it's h bar to the minus d times this rho 0 here. So you see the density is automatically very huge when you rescale the gradient with h bar. So it is a high density, and that's why we have to put this h bar to the d here in the equation. So we will be looking at the following F0s. So I will restrict myself to 3 special cases. So first, the Maxwellian. Okay, so E minus V squared minus mu. I write it in a I don't know how you want to put it. Maxwell-Boltzmann. Okay, so I'm introducing a temperature T, and instead of putting a constant in front, I'm introducing a chemical potential. It's just because I'm more used to it, but you can just put the constant in front instead if you like. We will also look at the Fermi-Dirac distribution, which for electrons is the one you should take into account, so that's Fermi-Dirac. For very large velocities, it's a bit the same as Maxwell, but for small velocities, it's different. And then we will also look at Bose-Einstein, which is the same, except it has a minus. And in this case, we will have to assume that mu is strictly negative to avoid any problem at zero momentum. Okay? Good. So now I guess you can guess what the theorem will be, or what we want to prove. So we want to show that if we start with an f, which is f0 plus small, something localized at least, then the dynamics makes sense, and maybe even goes weakly back to f0. And same here on the right side. And we also would like to know the link between the two theories in the limit h bar to 0. So dynamics of such infinite systems, I mean, this has not been studied very much. It's quite different from the usual case when f0 is 0, so when you don't have any reference. Usually one likes very much conserved quantities for these kind of problems, because you can use conserved quantities to kind of control your flow and show that the flow is not doing anything bad, and then show existence and global well-posedness, this kind of thing. So what are the usual conserved quantities? So if f0 is equal to 0, then for instance the number of particles is conserved. Okay, that's a typical thing. And the energy would be conserved, but for us they will both be infinite. And so of course, if you start with an f which is close to an f0, you could look at the difference between the two infinite quantities, and this will also be conserved. Okay, if it makes sense, it will be conserved. But this thing has no sign, as you can see, because you can remove or add particles to your gas, and therefore it will not help very much if it has no sign. Okay, the sign is very important when you want to control the flow. In the talk, I will try to explain that the energy is different by putting appropriate assumptions. One can use the relative energy, which is essentially the difference between the energy of F and the energy of F0, and which has a sign and which we can use to control the flow and get global well-posedness and so on. However, the energy will be the only conserved quantity at our disposal, and it's quite weak. For instance, it will not control the number of particles or the fluctuations in the number of particles. We will never be able to say that it's even finite. Okay, so that's why it's much harder than the usual situation, just because the conserved quantities are very weak. Somehow there is energy and nothing else. Okay, so now let me, how do I erase? This is something I have not...
I can help you.
Oh, this is the thing. So let me continue here. Okay, so what I will do now is just to state the theorems and then make comments. And then we can stop. When do I have to stop this?
About 1450 to 1465.
Okay. So let me just state a very long theorem which contains everything. Should I? Try it a bit. So the theorems will involve some quantities which I will only define properly later. So a theorem. We will only work in dimensions 1, 2, and 3, which for physics is okay, I guess. And I will assume that our interaction potential is very nice. So I will assume that it is integrable and bounded, and it has two derivatives which are integrable and bounded, just to make things easier. Oops. Okay, so integrable and bounded with two derivatives the same. Then I take F0 as before. as before, I mean one of the three examples. Good. So there will be first well-posedness for Vlasov, then well-posedness for Hartree, and then convergence Hartree to Vlasov. I mean, these theorems are not very surprising, and there will be no big surprise. I just have to tell you in which space this is true or not. Okay? So first, global well-posedness for Vlasov. So the whole point is to prove global well-posedness in the relative entropy space, which I will define afterwards. Okay, that's what I started to vaguely explain. So we will look at an initial state which has a finite relative entropy with respect to the gas. Okay, I forgot to say something important, that we will assume that W is a positive type to make sure the interactions do not do anything too bad. Okay, and then I will show that then there is a unique solution of Vlasov, which has a finite relative entropy for all time. Okay, so you take an initial F such that the relative entropy, which I will define afterwards, okay, if the gas is finite, then there exists a unique global solution to Vlasov F. So as usual, I mean, one has to be a little bit careful about the spaces. So it's going to be a perturbation of F0. So it will be F0 plus something bounded in time with values in L2 in phase space. Okay, so the fluctuation will stay in L2. This actually implies that the difference is in L2, and this will be conserved. And it's smooth, I mean not smooth, but continuous with values in distributions. I have to tell you it's continuous in some space to just give a meaning to the value at t equals 0. So f at t equals 0 is of course equal to the initial condition. And unique global solution in this space such that the relative entropy is uniformly bounded. Okay, so this is global well-posedness for Vlasov in the energy space. Except it's relative to your reference. Now there is a very similar theorem for Hartree. Okay, so maybe I can be a little bit vague. Hartree. Okay, so it's idem. Except, of course, that you have to use a quantum relative entropy. So you will assume that your initial gamma is a perturbation with a finite relative entropy. And then your unique gamma will be gamma 0 plus continuous in time. And then let me speak in terms of kernel. The kernel will be H1 if it's two variables. It's a little bit easier, then I don't have to speak about Chapman spaces and so on. And all the same, okay, so gamma at t equals 0 is the initial guy, and the H is bounded. And now the semi-classical limit. So to do the semi-classical limit, I have to consider a sequence of initial conditions. Okay, so now my initial gamma will depend on h bar. Okay, I'm not displaying this in the notation, but you know what I mean. And I will assume that h bar to the d times the relative entropy is bounded, and h bar goes to 0. Okay, in the limit h bar to 0. And I will also assume that the Wigner transform of gamma has a weak limit. Okay, so I'm assuming that the Wigner transform of my initial gamma has a limit, which I call f, the initial f. This limit could be very weak, so in the sense of distribution, that's fine. Okay. And then the conclusion is that the Wigner transform of the evolved gamma converges weakly to the f of t for all times, which is also in the sense of distributions. Okay, so you see it's a very weak convergence of Hartree to Vlasov. I think this can be improved a lot, but we didn't really try this. And then one can also look at the density. So if I look at the rho gamma of t, okay, so I look at the density. Remember that it's very big, so I have to multiply it by h bar to the d. If I subtract the reference rho 0, okay, this converges weakly to the rho of the f of t minus rho 0 in some LP space, so that's weakly in infinity in time with values in L2 plus L1 plus 2 over d in x. And in 1D you have to put 2. I mean, there's no second space in 1D. So that's the theorem. So people in the room can see the whole theorem, which has 3 parts. It's actually 3 theorems. But that's everything I want to discuss today. Okay, there will be nothing more. Online, I think you can at least see part of the global white closeness. That's okay. That's the results. So now I have to make many comments. I should have the rest of the other part of the little break. You can look at the theorem, prepare your questions. I'm sure you have plenty.
So I have a question.
Yes, go ahead.
Okay, so when you look at the result for the Vlasov, when you do the Wigner transform, now it's at the level of classical functions. So here, whereas so you don't have convergence in the you don't have the how should I say this? So your convergence is just weak, but you don't have some type of more relative entropy type convergence results, right?
No, so it's true that one could try to make this more quantitative, and the only the only quantity that could be used is the relative entropy. We've not tried this at all. It's just by compactness that we prove this theorem. And I will make comments. I mean, the assumptions are also not optimal for sure.
But then would you
Yes.
have it with the relative entropy, you would have it also in trace norm, because you have this inequality for which...
Yeah, but you have to be careful of this H bar which
yeah.
is floating around. So, I mean, L2 is Hilbert-Schmidt. There was an L2 somewhere, but trace norms usually go wrong. I mean, also, we made a choice. I mean, there are 2 ways. We've got 2 different worlds. So the quantum world, the classical world. And since we converge to classical, it's natural to look at the problem fully in phase space. But I mean, you could also try to take your Vlasov solution, put it back to the quantum, and try to compare it to the... I mean, quantization goes both ways. So. Okay, so let me make comments. I will tell you what's new and what's not. Except if there are other questions. Okay, comments. Lots of comments. So first, I mean, H and HCl, that's the relative entropy, which I will define later. This will be the first thing I will do after the comments. And they depend on F0. Right? So for mu T, and whether you do Maxwell or Fermi Dirac, there is a corresponding relative entropy. So it's really F0 dependent. The other thing is that W is the linear transform, so W h bar of gamma of xp is defined by gamma, and it's the usual linear transform, which many people know, but some maybe don't, so that's the definition. Okay, and Wigner is good because if you compute the linear transform of your gas, of the translation invariant problem, you get exactly L0 V. I hope I didn't screw up any H bar. I think it's okay. Okay. So now comments about the global well-posedness for Hartree. So the global well-posedness for Hartree is something we did some time ago already with Julien. So that's a CMP paper in 2015. And so to prove this global well-posedness, so the only thing you have to remember is that we used Strickard's estimates. And because we have this background, and the usual Strickard's estimates are not very useful, so we had to use, so using new, I mean I call them new because they didn't exist before, but now they are not so new anymore. So a few years back, new Strickard estimates due to Frank, myself, Philippe, and Robert Salinger. Actually, our motivation for the Strickards was because of this problem, which is James 2014. Okay, so on the quantum side, we use the Strickard's estimate to show a local well-posedness, if you like. And I would like to insist on the fact that the same Strickards are valid on the Vlasov side, but they don't seem to be useful. Or, I mean, we didn't find any way of using them. So Vlasov is much more complicated with respect to even local well-posedness. Right? It's much more singular in a way. So there are Strickards which were very useful in the quantum case, and we found no way of using them in the classical case. I mean, I think it's well known that it's difficult, but okay, so that's about the global well-posedness. I have to mention that scattering plus return to equilibrium, let me call it, so what do I mean is that for large times, the f of t, sorry, not the f of t, it's Hartree, the gamma of t goes weakly to gamma 0. It can only be weak because it's a Hamiltonian system, but weakly, somehow something disperses, disappears, and then finally you get your gas in infinite time, and you can even prove scattering around your gas. This we proved with Julien in 2014, but we could only do 2 dimensions because we used some special streetcards. And then it was finally solved by Thomas Chen on another chapter of it. In 2018 in all dimensions. Okay. So under appropriate assumptions, which I'm not going to discuss in detail, then for infinite time, your gas will return to equilibrium. The gamma of t will converge weakly to gamma 0 when t goes to infinity. So this is the Hartree part. So in a sense, this is not very new. It's 5 or 6 years old. Now Vlasov. So the global well-posedness for Vlasov in the energy space is new. In the relative entropy space, if you like. So there are not so many papers on this problem. There are many, but they all look at what people call Landau damping, which is the scattering and return to equilibrium. So it's Landau damping. So Landau damping is just the fact that if you do a small perturbation, let it evolve, it will converge weakly back to the gas. Okay, so it's exactly the same as here, with very similar assumptions, by the way. So this was proved by Bedrosian, Masmoudi, and Moreau. In 2018. And there's also a work by Quan Nguyen and Rousset in 2019. So of course, when you prove that it returns to equilibrium, you also show that the solution is well defined for all times. It's a byproduct of your theorem, but it's a much stronger theorem. And these two parts here are always for small perturbations. So you always start with a very tiny perturbation of your gas, and you show it goes back to equilibrium. So the global well-posedness I have stated here is for a perturbation of any size as soon as it has a finite relative entropy. Okay, so you have to think it's a local perturbation, but it could be very big of any height. Okay? And global well-posedness in this case was not known. It's actually mentioned as an open problem in this paper. How do we prove global well-posedness? Well, actually, we first prove the semi-classical limit, and then we get a solution of Vlasov by doing the semi-classical limit, which gives existence. So we get existence of a global solution in Vlasov by passing through the quantum world, if you like. And for this reason, we have very suboptimal or probably suboptimal assumptions for the Vlasov. So one would certainly expect a very similar theorem for a much more general class of F0, much weaker assumptions on W. But since we go through the quantum problem, we need more assumptions. And that's why I expect that the theorem is not at all optimal for Vlasov, but it's the first of this kind. Okay, so strong assumptions. Due to semi-classical limit, which is the way we get existence for Vlasov. After all, going through the quantum is one way of regularizing Vlasov. Maybe it looks complicated, but it's also physically relevant. The uniqueness for Vlasov we adapted to the case of positive density. So adaptation of the work of Grégoire Lepère. In 2006, where he was using some kind of optimal transport method. So what we did was to generalize his method to the case of if you like, things which are not, do not have a finite mass. So it's some kind of infinite mass optimal transport. You want to transport a measure to another measure, but they do not have a finite mass. Okay. And then some remarks on the semi-classical limits. So of course there are many works on the semi-classical limit, Hartree and Vlasov. But I think it's the first at positive density when you have this background. We have the experts in the room, so they can always contradict me. Okay, so but first at positive density. And I mean, these kind of weak limits only appear in very old works, so now people are able to really control the convergence much better, and I think it would be very interesting to try to do the same in this setting, but we have not tried. Okay, so now in the remaining 15 minutes or 10 minutes, something like that, I would like to quickly describe three tools which we use in, maybe I keep the theorem for the people in the room. So I have to define the relative entropy and tell you how. I mean, you should have complained. I'm a little bit disappointed. Nobody complained. You see, the Hartree and Vlasov equations, they contain the density. But when I wrote there is a unique solution, blah, 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 I mean, the conditions I gave, I mean, they are not clear that they imply that the density makes sense. So, one has to, so somehow the main part is to understand what is the relative energy telling us about the density. Okay? I have to take. Very fast. Okay, so we have to use, so to control the density, we use Vittian estimates, which are again due to Rupert. And this was a due 2000 something. 13. Maybe I state right away what is the bound before I finish the talk by discussing the relative entropy, just to define it seriously. So the theorem says, so it's the following. Let me state it with all the H bar. So you look at the relative entropy, which I will define shortly, and it says that this controls the density in some LP spaces. Okay? So in 1D, it's actually just rho gamma minus rho 0 squared, while 1 to 2D. And in higher dimensions, you have a control which is not the same when this difference is small and when the difference is big, so it's the minimum of H bar to the D, rho gamma minus rho 0 squared, and the same thing to the power 1 plus 2 over D. Okay, so the minimum means that when it's small, you get the worst of the two, which is the square. When it's large, you get the worst, which is the 1 plus 2 over D. That's the usual Tiering at large density. Okay, so this theorem here is telling you that when you have a finite relative entropy, actually you do have a density. But you see that this does not guarantee at all that the difference is integrable, for instance. So the difference could still have infinitely, they could still have be infinitely many particles between the two states. And you have a rather weak control, so it's essentially L2 and L1 plus 2 over D. But that's the main tool which we have to use in order to control the density and then pass to the limit. So now I have to tell you, to finish this talk, what is the relative entropy. Let me discuss this on the Vlasov part. Okay, so now I don't know what you know, but my experience is that surprisingly it's not that well known in utility theory, so let me discuss this for 5 minutes. So let me start with a case where you do not put any interaction, and maybe you do not work in the whole space just to make sure everything is finite. Okay, then F0, the F0 of V, is the unique minimizer of the free energy, which is the following. So you integrate V squared minus mu F minus T integral S of F. Okay. And integrate over both X and velocity. So your equilibrium state is minimizing something. Okay. And this S depends on the F you took. So the S of X is equal to minus X log X plus X. So that's the usual Boltzmann entropy. Okay. For Maxwell-Boltzmann, it's equal to minus X log X minus 1 minus X log 1 minus X for Fermi Dirac, and minus X log X plus 1 plus X log 1 plus X for Bose-Einstein. Okay, so each entropy has a corresponding equilibrium state. Or each equilibrium state has a corresponding entropy. So why is it so? Why is it minimizing this? Well, that's because all these entropies are concave. Be careful, my entropies are concave, not convex, because I have a minus here. So if I find any critical point of this functional, it has to be the minimizer because of the minus. So this is strictly convex. Okay, and what is the equation? It's really just V squared minus mu over T equal S prime of F0. Okay, so that's the link between F0 and S and your energy, if you like. Okay, so I know that F0 minimizes this free energy. So from this I conclude that if I have any F, and I compute its free energy minus the one of F0, I get something positive. And that's the relative entropy. Okay, so if you compute this free energy over there of some F minus the same for F0, you know it has to be non-negative because F0 is the minimizer. Okay, and that's the definition of H classical of F0. And if you compute what it is, usually we put a T here, so let me put a T. What is it? If you do the computation, you see, so I have this minus the same for F0, this minus the same for F0. Okay, but this here is S prime of F0. If I do the computation, I get S of F minus S of F0 minus S prime of F0, F minus F0. Okay, so for any S like that, there is a corresponding, any mu and T, there is a corresponding equilibrium state of 0, and there is a corresponding classical relative entropy, which is positive and vanishes only when F is equal to F0. And you see in this formula why. That's because S is concave, so this whole thing is negative, and you have a minus. Okay? So that's the relative entropy. Of course, there is a corresponding quantum entropy, which is minus T, the trace of the same thing. And as usual, on the quantum side, it's a little bit more complicated to understand this object, right? Because now they are non-commuting, so it's not an integral of something. It's something which we studied with Julien, as well as Andreas, together with Christian Heinzel and Robert in, I suppose, 15. Okay, so how to really give a meaning to this object and what does it control exactly, and then Liptier inequalities tell you that it controls some properties in terms of flow. So now you may be worried, I hope you're worried, because when W is non-zero, then clearly this looks different, because if you compute the corresponding energy, so it's going to be the same V squared minus mu F, but now we will have the nonlinear mean-field interaction. Okay, so that's the free energy, again in finite volume to make sure everything is well defined. So it's the same as before, but now I have the mean field energy. I have to stop.
3 minutes.
Okay, I will stop very soon. Okay, so I have this mean field and direct energy of my potential W. Let me notice that this is nothing but a constant times F Fourier transform squared times W hat of K dk. So you see that it's positive and convex. So the convexity is not lost whenever W is positive definite, which is why it was in the theorem. So you may just be worried that if I look, so this is still a convex function of F, if I look at a critical point, now it's nonlinear. Okay? However, the effect of the nonlinearity is just to renormalize the chemical potential. So if I write the equation, I get V squared minus mu plus rho, the rho of my F star W, but rho, I'm looking for something which only depends on V. Okay, so it's just a constant, and then integral W equal everything divided by T equal T S prime of F. Okay, and you see that it's actually a non-linear equation for F, but only through the density. So if you like, it's a non-linear equation for the density, or if you prefer, it's a non-linear equation for a kind of an effective chemical potential. Okay, so first, you think that you have to solve this non-linear equation and that things are going to be complicated. But the magic is once you solve this equation, okay, so the energy has a different mu from the mu of the F0. Okay, so the mu of the F is different from the mu you have to put in the energy. But then when you compute F of F minus F of F0, which is nothing, what is it that you get? There will be, I mean, you want to express this nonlinear term in terms of the difference between the rho of F and the rho of F0, and then there is a cross term, and this cross term is exactly this one. So everything simplifies. You get T H of F F0 plus 1/2 rho of F minus F0 of X, rho of F minus F0 of Y, W of X minus Y. And that's the last formula of this talk. It's very important. Yeah. Draw a box around it. So this is the relative free energy of your system, which is going to be conserved by the time evolution. And you see that it involves, so there was a problem with different mu's and so on, but this has completely disappeared right now. So it's the usual H, the same H I had here, okay, plus the interaction. But now if you assume that W is positive type, this is positive, and therefore you see that if this is conserved as you believe, then you have a sum of two positive terms, and therefore the entropy will be controlled. Okay? And the entropy controls some LP norms of rho, and these LP norms of rho control this term, and so it's all equivalent to controlling the relative entropy. Okay? So it's because of this formula here, and the fact that W is positive type, that you are able to prove a global well-posedness in the relative entropy space. And everything, the algebra is the same in the quantum case, as you can imagine. I have to stop. Thank you for your attention.
Thank you very much for this very clear talk. Any questions from the audience already? Yes, Robert.
So one question concerning the bosons, fermions, right? You sort of did everything at the same time, yet you didn't talk about the Pauli principle, and you used leap tearing, so...
No, because there is temperature. So with temperature, somehow F is going to be bounded.
Yes, but there's no additional assumption on your gamma needed for the initial condition?
No, that's right, that's right. But I think, so in the paper, we actually decided that gamma was less than 1 all the time. Okay. But I think just the relative entropy, or am I messing up the H bar maybe again? Okay, let's assume everything is bounded.
Also for the bosons?
Yeah, bosons too, because it's positive temperature. So if mu is negative, it's all bounded. And then leap tearing holds.
Sorry, what about the... So, I mean, this analysis works at positive temperature, right?
Yes.
And could you comment on the zero temperature limit? So this relative entropy, what does it become? Like a difference of kinetic energies?
It becomes the difference of kinetic energies, and then it's less nice to control. So although global well-posedness for Hartree will have it at zero temperature, the limit and the global well-posedness for Vlasov at zero temperature, because now F0 is singular. So it doesn't quite work. Also, I have not explained why we can only treat those F0s. And so we need some kind of generalization of the Berezin-Lieb inequalities in order to control the relative entropy on the quantum side with the relative entropy of the Houssimi measures. And this we can only prove for some very specific F0s, including these ones. So there is some kind of, I mean, when you want to pass from quantum to classical, somehow you need a lot on the quantum side because entropy is not so nice. You have all these traces of non-commuting operators. And everything should be much nicer in the classical case where you don't see these problems.
We have time for one more question.
Can I ask another question? So about what you were saying about the Landau damping and the results you were mentioning, so do I understand correctly, the available results are for small perturbations of equilibrium?
Yes, you assume that F minus F0 is small in some, some very small space. Okay, you ask some explicit decay in space, maybe even in velocities, I don't remember. And then you show that it goes weakly to the F0 for large times.
But your global well-posedness results instead they hold for a larger class of...
Yes, I mean here except I think they also have very strong assumptions on W. Okay, but otherwise it's just finite relative entropy, so it's much larger, and also it's not really small. Mm-hmm. I mean, it could be large but local. It has to be local for this to be finite. It has to be local. But, you could still. The difference could still not be non-integrable in principle, I suppose. But
okay, maybe we have still the opportunity for an online question if
there was
anyone
The chat is not
No, it's
something else.
yes.
If anyone wants to unmute and ask a question. No, okay, it seems we do not have any online questions. So our next speaker, thanks.
Thanks.